Okay, section 2, chapter 6, section 2 was about generators and motors. And we are going to use some basic information we learned in section 1 in this section. In fact, we are going to learn the devices which works by the principle of electromagnetic induction. And when I was talking about section 1, I said that this section is mostly about changing magnetic flux, because if we make a change in magnetic flux, we can induce an EMF in a loop or coils. And we can change magnetic flux by 3 ways. One of them is changing magnetic field strength or its direction. So magnetic flux changes. Or moving the loop into and out of the magnetic field by moving a loop inside into and out of the magnetic field. We are changing effective area of the loop, which means the area which is perpendicular to the magnetic field is called effective area. Or third one is by changing the orientation of the loop with respect to the magnetic field by angle. We are changing the angle. When angle changes, also magnetic flux changes. And we say that this third method is effective, practical. And rotating a loop inside a magnetic field is practical than first and second. That's why several types of generators are using this technique. And we are rotating a loop inside a magnetic field. As the loop is rotating, magnetic flux through the coil is changing. As magnetic flux is changing, we induce an EMF and induce a current. And these devices, which converts mechanical energy, because as the loop is rotating, of course it has mechanical energy. As it's rotating, we get electrical energy. So this device, which converts mechanical energy to electrical energy, is called generator. They are called electric generators. We are going to study in details how this happens. And the mechanical energy which we convert to electrical energy is rotational mechanical energy. So we are going to rotate the loop somehow inside the magnetic field as the loop is rotating. So we are going to induce a current. We will get a current, we will get electrical energy. That device is called generator. And as I said, we should first rotate a loop inside a magnetic field. There are a few methods to rotate a loop inside a magnetic field. Of course, you cannot rotate it by your hand. So we should find a technique and way, and a practical way to rotate these loops inside a magnetic field. 2 methods are told in your book. One of them is using water, hydroelectric plants. Second one is using coal or natural gas plants. In hydroelectric plants, you are going to cut a river, and you are going to accumulate the water, and then after that you are going to open a gate on the wall of this barrier, and then this water will start flowing out with a big speed, and then strikes the blades of a device called a turbine. And turbine, because of the water strikes the blades, it starts to rotate. After the turbine is attached to generators, coils, this is generator. Coils of generator starts to rotate inside the magnetic field, and then we change magnetic flux through the coil, and we get EMF or electric current, and then send to seconds. One of them is this. Second one is we can use coal or natural gas burning plant. Natural gas is clean, coal is a little dirty and polluted environment, but natural gas is much cleaner. So how we use the system? The system is like that. There is an oven, you are going to burn the coal or natural gas. And inside this pipe there is some water, it is closed circuit. And in here we are going to burn the gas, and then this burned gas will heat the water up and its temperature increases. Then, when temperature increases, convert it to steam. And from water it changes to steam. After that, steam starts to blow against these turbines like that, like a wind blows against a windmill. This turbine starts to rotate. And after that, you are going to attach this turbine to generator's coil, and coils of generator will rotate. As coils of generator rotates, it induces the magnetic flux through the coil is changing, so it uses a current and make EMF, and then we are going to get it in houses. So these two are the systems, the methods which are explained in your book, but of course there are other alternative methods. So wind is also can be used for rotating the generator's coils, and windmills can be used also for producing electricity from wind. So the basic idea is rotate the generator's coils inside a magnetic field by some method. What method you are going to use is up to you. So turbine's rotational motion, as turbine is rotating, is transferred to what? Coils of the generator. And the coil starts rotating in a magnetic field. So as coil is rotating in a magnetic field, angle theta is changing. And also we say that the still change in angle theta as the coil is rotating, effective area. What is effective area? Effective area is the area of the coil perpendicular to magnetic field. If I write an equation for it, it's A times cosine theta. It is the area of the coil perpendicular to magnetic field. This A cosine theta, yani effective area, is continuously changing. And as it is changing, magnetic flux is changing. So if the magnetic flux changes according to Faraday's law, which law? We know that is equal to negative m delta phi over delta t. So because magnetic flux is changing as effective area and theta changes, so the change in magnetic flux induces an EMF, induces a current. And this induced EMF is going to have a function. This magnetic flux also has a function, trigonometric function, because it's cosine. You see that. Instead of omega, pardon, theta, I can write its equivalent in chapter 1, section 1. We'll talk about this. So omega was equal to delta theta over, when the cross product, we'll get delta theta as delta theta is equal to omega times. This is for average value. For instantaneous values, we are going to remove thetas, these deltas. Then theta is going to be omega times t. And instead of theta, we can write omega times t. And in this case, magnetic flux equation is going to be like this: B times A times cosine omega t. And as time goes, magnetic flux is changing as the loop is rotating inside a magnetic field. And we are going to take the derivative of magnetic flux function, because the delta phi over delta t in fact defines the derivative, and you know that the derivative of cosine function is sine function. When we go with derivative, we are going to get another equation for induced EMF. This equation is, it's a sine function, sine omega t, but this sine omega t will be multiplied by a, b, a, and also n, which is coming from in here, and omega is coming from out, so it becomes b, a, and omega. And in front of sine function, we are going to put a constant. This constant is maximum value of this induced EMF. Yani, induced EMF instantaneously changing between two maximum values. One of them is positive B, A, and omega. The other one is negative B, A, and omega. Okay, so E is equal to B, A, and omega. Yani sometimes we say Banu sine omega t is the equation for induced EMF, how output of an AC generators is in terms of sine function. This equation describes sinusoidal variation, yani it's changing as a sine function. Because of that, it says sinusoidal variation. Yes, it's a variation, but as time goes, induced EMF is changing. This E equation is sinusoidal variation of EMF with maximum value. How much? BAN omega, yani E max is in this equation. But these E values continuously changing. 0 increases, maximum decreases, 0 increases, maximum decreases. So this E is called instantaneous value. Because this value is changing by time. If a quantity changes by time, what do we say it? Instantaneous value. This E is the instantaneous value of this EMF. As you say, it's continuously changing. But E max depends on B, A, N, and omega. If you don't make a change in them, E max stays unchanged, just like this. So, this is the equation, the graph of an AC EMF, of an AC generator. As you see, it's changing between positive value of the E max and negative E max. It is maximum value. As time goes, is the same. But instantaneous value is continuously changing. Positive decreases 0, negative increases, maximum decreases 0. And one positive, one negative. One positive, one negative. This positive and negative indicates direction of the induced current and also polarization of induced EMF. They are changing continuously. The direction of induced current is continuously changing, but not only direction, also magnitude. And here 0, then increases, then maximum, then decreases, and 0. So then we say that direction of the induced current regularly, positive, negative. And also magnitude of the induced current continuously changing. Increase, maximum, decrease, 0. Increase, maximum, decrease, 0. This changing current or changing EMF is called as alternating current and represented by AC, alternating current. And Banu indicates or calculates maximum value of induced EMF. In here, B is magnetic field of the magnet inside the generator. When you pack a generator, you cannot change this anymore. Area of the coil, when you pack a generator, you cannot change area too. Number of turns of generator also cannot be changed. Only we can make a change in omega if you want to rotate generator coils faster. Maximum value of this EMF, what happens? Increases. But if you increase omega. But for many generators, this omega is constant, unchanged, standard. Yes, this omega.
Or just like, it's not for only the...
No, if you want, you can change it. It is not a problem. You can change it. But because devices, yeah, in one question I said in quizzes, remember it doubled. If omega doubled,
but we can't change it.
We can. If you want, we can. Who can stop us? But if you change it, that's the problem. Especially if you are doing houses. Maximum EMF increases, and then it can cause some damage in the machines in your house. That's why EMF values are kept, maximum EMF values kept unchanged for a generator. Okay. So BA and omega is calculated by 2 pi. I've also been calculating this in chapter 1, section 1. And this omega is sometimes called angular speed. In section 1 we learned rotational speed. And now in this section also one more added, angular frequency. And omega also named as angular frequency, which is radian per second per unit. And how quickly this alternating current is changing defines the frequency of this alternating current. And this is the definition of the frequency. This alternating current undergoes one full cycle of change in direction 50 times each second. Yeah, what is one full cycle? One full wave. This is one full cycle, one full wave. Another full cycle, another wave. In 1 second, how many waves are there? Anybody see? 50. There are 50 waves, 50 cycles, which defines frequency of this alternating current. And almost all generators in the Iraq or Turkey or Asia all have the same frequency, 50 hertz. United States and Canada, they have different frequencies, 60. Okay, this statement defines frequency of an AC generator. What is it? The alternating current undergoes one full cycle of change in direction 50 times each second. This definition defines that frequency of this alternating current is 50 hertz. And this is the structure of an AC generator. If you provide these 4 components, you can make your own generator. One of them is absolutely you need a magnetic field. And magnetic field is provided by magnets. So a magnet with N pole and S pole. Between this N and S pole, you are going to put a loop or coil. So first component is magnets. Permanent magnets, providing magnetic field. Second component, you have to put a loop inside this magnetic field because you are going to rotate it. As you are rotating, magnetic flux is changing, so we induce EMF. So conducting loops, free to rotate in a magnetic field is the second component. Third component, each end of this loop is attached to a ring. So right end is attached to first ring, left end of the loop is attached to second ring. Each end is attached to a ring, which is called slip rings because they are rotating, slipping. on that device called as brush. Two conducting rings called slip rings attached to each end of the loop and rotating together with the look. Yani loop is rotating. This loop is rotating, so magnetic flux is changing. These rings are also rotating. If the loop is rotating clockwise, rings are rotating clockwise. And this is the third component, slip rings. Fourth component is brushes. What is brush? Soft carbon, graphite. They are in contact with the rings to take the electric charges from the ring to the external circuit to the lamp. Yani this brush function is to take the electric charges from the ring, give it to the lamp. But there are two brushes, but these brushes are fixed. Brush A, brush B. Brush A is always in contact with the first ring. Brush B, always in contact with the second ring. That's why as the loop is rotating, magnetic field to electric current direction is changing, so electric current direction on external circuit also changing. One positive, then negative. One positive, then negative. One positive, then negative in here. Yani to the right, to the left, to the right, to the left, to the left, and vibrating electric current on the lamp. This is AC. Okay, these are the structures of a general, essential structure, components of an AC generator. Clear? Now, we know that as this loop is rotating inside a magnetic field, what's happening? The induced EMF is continuously changing. At some position of the loop inside a magnetic field, this induced EMF is zero. At some position, it is maximum. At some position, it's decreasing. At some position, it's increasing. Now, we are going to talk about this. At what position of this rotating loop of the generator inside a magnetic field, induced EMF gets maximum and Y? At what position of this loop inside a magnetic field, induced EMF is 0 and Y? So, variation of EMF of a rotating loop of an AC generator. So, we are going to rotate the loop inside a magnetic field. This is what it is. As you see, from M pole to S pole, magnetic field lines are formed. From right to left. And there is a loop. There is a loop inside a magnetic field. Loop is rotating inside a magnetic field according to given picture, counter clockwise. As this loop is rotating, of course, its orientation will change. Now I will start with the orientation which is parallel, and the loop takes a position parallel to the magnetic field lines. As loop is parallel to magnetic field lines, normal of the loop, which is green line, is going to be perpendicular to magnetic field lines. Loop itself is parallel, but normal of the loop is perpendicular to magnetic field lines. And in this EMF equation, E is equal to E max sine theta. This theta is the angle between normal line of the loop and magnetic field lines. How much is this angle? Now, 90. Now let's put inside this equation. If sine 90, angle is 90 axis orientation between normal and the magnetic field lines. Sine 90 is 1. If we write in here 1, so we'll get E is equal to E max. Maximum induced EMF in this loop, at this orientation. When a rotating loop takes a position parallel to magnetic field lines, at this position, at this orientation, induced EMF of the loop is maximum. We can also go by this way. Sometimes you ask a teacher, at this orientation, magnetic flux is 0, but how could it be induced EMF is maximum? We are not looking magnetic flux. We are looking change in magnetic flux. Yes, magnetic flux instantaneous to 0, but change from 0 to a number, it's the greatest change in here happens. When it was parallel, 0. Relative change from 0 to a number, it's a big change. Rate of change of magnetic flux at this orientation is maximum. That's why induced EMF is maximum, even though instantaneously magnetic flux is 0. Okay. Know that we are not looking for magnetic flux. We are looking for change in magnetic flux. Change in magnetic flux is maximum. That's why induced EMF at this orientation instantaneously maximum. Okay. What about as this loop is rotating? Of course, Angle between normal and magnetic field lines will change. And finally, it will take a position, loop will take a position perpendicular to magnetic field lines, but the normal of line is going to be, normal of loop is going to be the same direction. So now what is the angle between this magnetic field vector and normal line? 0. They are in the same direction. If two vectors are in the same direction, so angle between them is 0. So if angle is 0, which is angle between B and N, if 0, they are in the same direction. In this case, sine 0, 0. Then when we write 0 in this equation instead of sine theta, so induced EMF becomes 0. The induced EMF at this orientation is 0. Yani when the rotating loop takes a position which is perpendicular to magnetic field lines, at that moment, induced EMF becomes 0. But still we can think this way. Okay, teacher, induced EMF is 0, but magnetic flux is maximum. Yes, I say magnetic flux is maximum. But we are not looking at magnetic flux. We are looking at change, rate of change of magnetic flux. If magnetic flux is maximum, but rate of change of magnetic flux at that position is 0. Because as it's rotating very little, there is no big change. There is no change in the magnetic flux, very little rotation. If no change in magnetic flux, induced EMF 0. And also, be careful about this. Don't get confused with the section 1 case and this case. In section 1, we were pulling a loop from outside to inside of the magnetic field to induce a current. You should hold the loop perpendicular. If you hold it parallel, magnetic flux change is going to be 0. But this case, we are not taking the loop from outside to inside. We are rotating the loop inside a magnetic field. In that example, when we are pulling a loop from outside to inside, we are changing the effective area, not angle, we are changing the area, but in here we are changing the theta. That is difference, okay? So be careful. If you are taking a loop from outside of magnetic field to inside, you shouldn't hold it parallel to magnetic field lines. Otherwise, magnetic flux change is going to be 0, induced EMF is going to be 0. But in here it's different. When you are rotating a loop inside a magnetic field, so when it is perpendicular, rate of change of magnetic flux is 0, that's when induced EMF is 0. When it's parallel, rate of change of magnetic flux is maximum, induced EMF is maximum. Okay. So section 1 case and the section 2 cases are different, okay? What is key? Rotating. When rotating is section 2. Moving, pulling from outside to inside, inside to outside, it is section 1 cases. They are opposite. Okay, then this is how AC is changing. The AC EMF is changing for a generator's output. And also we can predict how is the orientation of loop inside a magnetic field at these points A, B, C, D, E, F, G, H. So B, D, F, H. Induced EMF is maximum. Induced EMF of a rotating is maximum when the loop is taking a position parallel to magnetic field lines. Yani this case. B, D, F, H. The loop, plane of the loop is parallel to magnetic field lines instantaneously. So induced current is, induced EMF is maximum. But A, C, E, G. A, C, E, G. At these positions, induced EMF is, at this point, induced EMF is 0. Then this rotating loop must take a position which is perpendicular to magnetic field lines. So the plane of the loop must be perpendicular, so induced EMF is 0 at G, E, C, A. And this is one of the exam question. Okay. This is all about AC generators. Now we will continue with direct current DC generators. Direct current generators are generally used in automobiles. They are not very frequently used in our life, just automobiles are using them. These direct current generators and AC generators are slightly different. Slightly. 3 components are same both AC and DC generators. They are common components for AC and DC generators. That permanent magnets both means magnetic fields. conducting loops. You should rotate loop inside a magnetic field, so that's why you need conducting loops. And also you need brushes to get the charges outside to the circuit. Yeah, and these are common in both AC and DC generator, but two components are different. Two components are different. One of the in AC generator we have two slip rings. Right end of the loop is attached to one ring, left is attached to second ring. These rings are in contact with brushes A and B. This is what AC generator is. Two slip rings we have. But in DC generator, instead of two slip rings, we have just one ring. But this one ring is divided into two segments, two halves. One end, say the right end of the loop, is attached to one segment, first segment. First segment is in contact with brush A. Left end of the loop is in contact with second segment. Second segment is in contact with brush B. In AC generator, this brush A is always in contact with the first ring, always in contact with the right end of the loop. Brush B is always in contact with ring 2, always in contact with the left end of the loop. But in AC generator, it's not like this. As this loop rotates 180 degrees, this one goes other side, 2 comes to the right side. Segment 1 gets in contact with B, segment 2 gets in contact with A. Yani they are changing, they are shifting. So brushes are in here, in DC generators. Brush A is once in contact with B, then with 2, then with 1, then 2, then with 1, then 2. But in here, no. A brush is always in contact with ring 1, always in contact with right end of the loop, same end. Brush B always in contact with ring 2, always in contact with the same side of the loop. But in here, as I said, so when we rotate this split ring, this one goes in here, 2 comes in here. So this split slip ring is called as commutator. In DC generator, we have split slip ring called commutator. Yeah, just one ring divided into 2 segments. And each end of the loop is attached to one end of the segment of the commutator. Yeah, as you see in here, the loop is rotating, so clockwise, and right end is attached to one commutator. Is attached to now brush A, left end is attached to one segment of the commutator, and then attached to another brushes. But why do we use this commutator? Commutator is the device which alternates, changes electric current direction in the loop when it's given to the outside. Like this, look at that. First note one thing. When you are rotating a loop inside a magnetic field, it doesn't matter if it's an AC generator or DC generator, these loops output is always AC. Always. Yeah, one part is positive, other is negative, then positive, then negative, continuously. This is changing. Output of this loop is always AC. But as this AC current passes through commutator, it inverts this negative part. Yeah, it was negative, huh? This negative part is converted to positive. By what? Commutator. Commutator does this. So, as the coil rotates, AC EMF is induced in the coil. Always in the coil we have AC. But commutator, as this AC EMF or AC current passes through this commutator inverts negative part of AC current in the loop as positive to the external circuit. Yeah, by means of commutator, we are going to get a pulsating magnetic current, like this, like a pulse. 1, 2, 3, 4, all are positive pulses, never negative. Or all are negative, never positive, one directional. So then the question, which of the following component of a DC generator converts AC EMF in the loop as the pulsating direct current in the outside? Commutator does this. Okay. This is what the pulsating direct current is. As you see, negative parts are cropped or shifted to what? Positive. Another negative change to positive. Another negative change to positive by means of commutator, and we get DC generator's output after commutator. But as you say, it's not perfect DC. It's pulsating DC. Yeah, 0 maximum, 0 maximum, 0 maximum, 0 maximum. We can do it much better than this by using more than one coil at different orientations or more than one loops like that. And in here, as you see, loop A, say the magnetic field is like that. This one, magnetic field. One loop is now parallel to magnetic field lines, while the other one is perpendicular. Which one's parallel? Loop A. So when these loops are rotating counterclockwise or clockwise, loop A's EMF is at that orientation is maximum. And blue is maximum. But red, loop B, 0. After 90-degree rotation, quarter rotation, red becomes horizontal, blue becomes vertical. Red becomes maximum, blue becomes 0. As you see, always we have one maximum. When we add them as a method, which is superposition principle we use for waves, this is also a wave, we are going to get this green curve, or what they say, green line, which is much better compared to blue, much better compared to red. This is the resultant EMF, and sum of the EMF of loop A and loop B. If you use more loops than 2 or 3 or 4 and 5, it's going to be much better. Then it's going to be almost a straight line, like a not perfect battery direct current. We should use some other devices to make it perfect current direct battery, but this is better than blue, better than. So by using more than one loop, 2, 3, 4, 5, a steadier, close to a DC direct current, steadier direct current can be produced. So this is all about the direct current, yani DC generators. And last device was motor. Remember I said that how many times there are different types of motors, but we are going to study DC motors. Direct current. They are motors that work with direct current and battery. We are going to connect the motor to battery, so it will start rotating. First, DC motors and DC generators are equal in structure. Permanent magnets, they have both have permanent magnets. Both have conducting, both have brushes, both have. Yeah, a DC generator can be used as a DC motor. A DC motor can be used as a DC generator. But their definitions are different. Generator converts mechanical energy to electrical energy, we get electricity. But in motor, we do opposite. We give electrical energy and with the battery, it starts to rotate, and their definitions are different. Even though DC motor and DC generator are equal in structure, their definitions are different. What they do is different. A motor converts electrical energy to mechanical energy. But how? By using an external battery. External battery provides electric current to the loops of the motor. External battery provides electric current to the loops of the motor. So then there will be two magnetic fields. One magnetic field already exists, which is permanent magnetic field of the magnet. The second magnetic field is as electric current is provided by this battery. So by means of the brush and the commutator and through the loop, of course this loop produces its own magnetic field. There will be two magnetic fields. One of them is the magnet's magnetic field, the other one is coil's magnetic field. So this current produces a magnetic field in the loop which is perpendicular to the plane of the loop. If the loop is horizontal, its magnetic field will be vertical. Then permanent magnetic field and loop's magnetic field start to push one another. They repel each other because they are crossing right now. No two magnetic fields wants to cross. So the fixed magnetic field of the permanent magnet repels the magnetic field of the loop, and loop starts rotating. Then, now let's attach a battery to this loop. So positive terminal, negative terminal of the battery like this. When we attach a battery to a loop like this, electric current will start from positive terminal, pass through the loop, and leave, and then negative terminals will come. Now there are two magnetic fields. Magnet's magnetic field in horizontal, loop's magnetic field in vertical. So this loop will tend to rotate? It was one of the mystery questions of 5-2. At what orientation of a loop inside an external magnetic field it will not tend to rotate? Perpendicular. What orientation it will tend to rotate? Any orientation different than perpendicular. Yani parallel. This loop will tend to rotate. Will start rotating until both magnetic field becomes in the same direction. Yani at this position. Until this position. At this position, it will stop rotating. But motor must continue rotating. How can we do it rotating? If we change electric current at this orientation, so magnetic fields will be opposite, they will continue repelling each other too. So then, fixed magnetic field of the loop magnetic field are now in the same direction, so loop does not tend to rotate. Then at this location, again commutator. Commutator alternates electric current direction in the loop, and loop's magnetic field becomes opposite, then red magnetic field. Continue pushing the loop's magnetic field, and loop will continue rotating. Then we can say two questions in here. So which of the following device of the DC motor alternates electric current direction when the loop is perpendicular to the magnetic field? Commutator. So what does commutator do by this way? Provides continuous rotation of the loop. Okay. But as this loop is rotating, these coils are rotating inside the magnetic field, another surprising thing happens. In fact, we know from chapter 6, section 1. What is it? As the loop of the motor rotates in the fixed magnetic field of the permanent magnet, so magnetic flux through the loops is changing. Yeah, when this loop is active position, magnetic flux is 0 through the loop. And now in here, maximum, if magnetic flux changes in a loop, what happens? It acts a kind of generator. And it also induces EMF. So motor, as motor's coils are rotating inside a magnetic field, magnetic flux through the loops of the motor is changing, so an EMF is induced in the loop. This EMF is the EMF what we know as we rotate the loop inside a magnetic, no different than that. But it's named in this title as back EMF. Back EMF. Why is it called back EMF? Because battery's electric current direction, which is in the direct drawing is clockwise fashion, and this motor's EMF electric current directions are opposite in direction. So the EMFs have opposite polarity. It acts to reduce the net electric current of this circuit. So A back acts to reduce the electric current in the loop of the coil. That's why it's called back EMF. Yani back, opposite, like opposite. And this back EMF is no different than induced EMF, what we know in the first title, Bağımlı sin omega t. So it depends on Bağımlı. So if I want to calculate net EMF provided to this motor, I have to subtract these two EMF because their electric currents are opposite. Net EMF is represented by V, which is the potential difference supplied to the motor, equals to what? Difference between them. I'm going to subtract that. Which one should be subtracted? Of course, E back must be subtracted because E back is always less than E in a real system, real motors. So I am going to subtract back EMF of the motor from EMF of the battery to calculate net EMF of the motor. Yeah, the potential difference supplied to the motor V net EMF is equal to the difference and subtraction of applied EMF of the battery minus back EMF of the motor. Yani V is equal to E minus A back. This E is unchanged. It depends on the battery's EMF. This is battery's EMF. Whatever the battery's in this value is, this is that number. But E back can change. Because E back is an induced EMF. Induced EMF depends on 1, 2, 3, 4 factors. B and A. These are unchanged because B, the motor is already packed. But omega changes. As omega changes, E back changes. Yani greater omega, greater E back. First, this is several times I can use your question. As motor starts rotating faster, what happens to the back EMF? Back EMF increases. One of them is the second. If back EMF increases, because battery's EMF is unchanged, it is the number for the battery, 1.5, 2, whatever. If E back increases, net EMF should decrease. Net EMF should decrease. Yani as E back increases, potential difference supplied to the motor, yani net EMF is decreasing. As net EMF decreases, according to Ohm's law, R is for a motor is the same, it's unchanged. If V decreases, I must decrease. And electric current supplied to the motor also decreases. And remember, we'll make a table in the lesson. Omega, E back, V and I. As omega increases, yani the motor rotates faster, E back increases. If E back increases, V. If V decreases, I. Yani first 2 increases, last 2 decreases. Or vice versa. If omega decreases, E back decreases, then V increases, I increases. And last title is the mutual inductance. Mutual inductance is a very easy one. In fact, it's the principles of transformers. In section 3, addendum section, we talk about this. It was the first electromagnetic induction experiment done by Michael Faraday. What was the experiment about? There were 2 coils which are not electrically connected. There's an iron ring. Around the iron ring, these coils are located. One coil is attached to battery, which is called primary coil. And there's a switch to control the circuit. Other coils connected to galvanometer. As we are changing the electric current in the primary coil, magnetic field in the primary coil is changing. Iron core guides the electromagnetic field lines, makes them circulating on this iron ring. And then magnetic flux through the secondary coil also changes. As magnetic flux on a coil changes, what happens? It induces EMF. So when initially the switch is open, electric current is 0. Magnetic field in the primary coil is magnetic flux in the secondary coil is 0. And you switch it on, you close the switch. Electric current jumps to a maximum value. Magnetic field in the primary coil jumps to maximum value. Magnetic flux in the secondary coil jumps to a maximum value. There's a magnetic flux change. Magnetic flux change induces a current in the coil, and then galvanometer star deflects in one direction. At the moment you switch it on, it deflects. Right or left, depending on your connection. But if you keep it close for a long time, this time, electric current stays unchanged, constant. Magnetic field stays unchanged, constant. Magnetic flux stays unchanged, constant. Again, constant magnetic flux. Induced EMF is 0. If you keep it close, the induced EMF, yani induced current in the secondary coil becomes 0. But when you switch it off, open the switch. This time, electric current decreases to 0. Magnetic field in the primary coil decreases to 0. Magnetic flux in the secondary coil decreases to 0. Is a change in magnetic flux? Yes. If increase in magnetic flux deflects to right, decrease in magnetic flux deflects to the left in the galvanometer. And equation for calculating induced EMF in secondary coil no different than, not so much different than the self-induction. Self-induction was negative L delta I over delta T, but in here it is negative M delta I over delta T. Again, due to the electric current changes in induced EMF in secondary coil, but we are changing electric current in primary coil, not in the secondary coil. We are changing electric current in the primary coil and induced EMF in the secondary coil because of the magnetic flux change. This capital M is called mutual inductance. Its unit is just like self-induced coefficient of self-induction, it's 100 again. But this M can be changed depending on some parameters. One of them is specification of the coils, length, number of turns, cross-section area of the 2-coil system, because there are 2 coils right now, not single. And one more thing, orientation of 2 coils with respect to one another. Like what? Mutual inductance is maximum when the coils are held parallel to each other. When you hold them parallel to each other, magnetic field lines leaving one coil passes through, second coil maximum magnetic flux change happens. But if you hold them perpendicular to one another, magnetic flux through the secondary coil is going to be not that maximum. It's going to be minimum. That's why mutual inductance becomes minimum for when the coils are perpendicular to each other. As I said at the beginning, mutual inductance is the basic of usable electric devices called transformer, which we studied in 6.3 the last time. I think section 2 is this all. Bitirdik.